In this video, we're going to talk about now a shortcut for taking the derivative, because obviously nobody has time to use the definition all the time. So remember the definition of the derivative. It's the slope of a tangent line at any given point. So here are some different rules. The derivative of a constant is 0 because the slope of a constant is 0. A constant would have a graph that was horizontal. Its slope is always 0. The power rule is the big one. So this is the one we're going to use all the time. This is what we call the shortcut. So we take our exponent, we bring it out front. That's why there's an n there. X stays the same. And then we take that exponent and we subtract 1 from it. If we have a coefficient that does not have an x in it, it's not a function, it's a number, it just kind of hangs out, and then we take the derivative of the function. If we have a sum or a difference, we take the derivative of each piece and we carry down the addition or subtraction. This does not work for multiplication and division. The derivative of sine is cosine. The derivative of cosine is negative sine. And finally, the derivative of e to the x is e to the x, so it stays exactly the same. So up here, our first example, we're just finding the derivative. We use the power rule because everything is written as a power. So 3 comes in the front, x stays the same. We subtract 1 from our exponent. In the next example, our exponent's a 1, so we multiply. X is now to the 0 power, which is just 1. 2 times 1 is just 2. So that guy goes away. Another way to think about it is this is a linear function. Its slope is 2. We must label that, but that's it. That's our derivative. So in order to use that, which is called the power rule, we have to write our terms as powers. So it's got to look like variable with some numerical exponent. So in example 2 here, we have radicals, and those need to be written as powers. So we're going to rewrite the original function. Radicals turn into rational exponents. Whatever our exponent is up here, in this case it's a 1, goes in the numerator. And our index goes in the denominator. Same deal here. We have 5. It's x to the 1 over an index of 2 because it's a square root. Now we're going to take our derivative following the same power rule. So 1/3 is our new coefficient. And then we have to subtract 1 from this guy. Here, we'll take half of 5, which is 5 over 2. And we'll subtract 1 from our exponent. And this is the derivative of g. Here we're going to find the derivative now. So when we find the derivative, remember, if it's a coefficient, it just drops down. The derivative of sine is just cosine. We cannot differentiate a quotient at this time. So we do need to rewrite this function. There's a 1 in front of it. So we're going to kind of separate this fraction into 1/4 times the cosine of x. So all I'm doing is I'm taking the fraction out front and I'm putting the cosine to the right of it. Now we can take the derivative. The 1/4 is a coefficient, so it's going to drop. The derivative of cosine is negative sine, so we need to make sure we have that negative way out in the front, so it doesn't look like 1/4 minus sine. And example 3, the derivative of 2x is just 2. The derivative of sine of x is just cosine of x. So this is a lot of information. First of all, we call the first function our position function. That tells us where we are located. So if we're in a real life situation, maybe our height. Where is our height? Our velocity is the first derivative. Sorry, that's a typo. First derivative of the position function. And it's our velocity. That tells us how our position is changing. Our second derivative is called our acceleration, and that describes how our velocity is changing. At each level, it describes what the previous level is doing. So again, it describes the change of its original. So we can think of the second derivative really as the first derivative of velocity. Speed is the absolute value of velocity. Velocity is both speed plus direction, and speed cannot be negative. If speed is increasing, that means velocity and acceleration have the same sign, so they are working together. So if they're both negative, two forces working together will create an increasing speed. If they have different signs, one maybe is going in the positive direction while it has a negative force on it, so its speed will be decreasing. Our position function looks like this. You've seen this all throughout middle school and high school. This is our initial velocity. This is our initial height. We do use 32 feet per second for acceleration due to gravity, or 9.8 meters per second. So right now we're just writing an equation of a tangent line. So remember, a tangent line is a straight line. So we're going to use point slope form because we know our point of tangency, and if we find the derivative of this function, then we will know the slope. Okay, so we can find the entire equation now. So the derivative of this, if we bring the 5 down, if I multiply by 5, those will cancel, and I'll be left with 2x to the 4th. Here, the 4 will come down. I'll get 4x to the 3rd. Here, the 2 will come down. I'll get 6x. And then the derivative of -1 is 0. So this will give me the slope of the tangent line at any given point. And for this particular given point, my x value is 5. So I need to plug in 5 in order to find the value of the slope. I'm going to cheat and use a calculator because that's going to be a big number. So we have a slope of 1,780. That's the slope. So now I'm just plugging in my values. So y minus the y value equals my slope. And then I'm going to have x minus the x value. And that will give me the equation to the tangent line at 5, -3.